All right, welcome to Triangle Similarity. This is 8.3 in your books, and we are just plowing through this unit. I know you're as excited about it as I am. All right, now the thing I want you to remember here more than anything is that we are proving triangles similar, not congruent. The only thing that's congruent in any of this are the angles. So keep that in mind. All right, our objective, we have but one: to use several methods to prove that triangles are similar. That's it. Okay, so we're going to give you a whole bunch of different ways. Okay, a lot of it is going to be like what we did to prove triangles congruent. Okay, but there is going to be the difference that we're just proving them similar. So keep that in mind, all right? All right, we're going to start off with a postulate. Okay, this goes along with like angle, side, side, all that good stuff. All right, so if there exists a correspondence between the vertices of two triangles such that the three angles of one triangle are congruent to the corresponding angles of the other triangle, then the triangles are similar, and that is by angle, angle, angle. You will not use this very often, okay? Keep that in mind. But if you are lucky enough to be given that you have two triangles and all three of their angles, well, each pair of three angles are congruent, then you have enough to show that they're similar, okay? Remember, we're not talking about congruence, so the lengths of the sides can be whatever, but it's the angles that are important. Okay, let's start off with this. We are given that angle B is congruent to angle E, and angle A is congruent to angle D. We would reach the conclusion that triangle ABC is similar to triangle DEF. Similar. Okay, that's similar. Remember, not congruent. Congruent has those extra lines underneath. Okay, and how can we do this? Well, this kind of goes along with that no-choice theorem. If we have two angles in each triangle, we've got two pairs of angles that are congruent, then by the no-choice theorem, that third one, C, has to be congruent to the third one over here, F. And that's by the no-choice theorem. But now, in similarity, we can just shorten it to Theorem 62. If there exists a correspondence between the vertices of two triangles such that the two angles of one triangle are congruent to the corresponding angles of the other, then the triangles are similar, and that is by angle, angle. Okay, the difference between this and the no-choice theorem. You're going to use the no-choice theorem when you're proving triangle congruence. When you're proving similarity, use this one. Use angle, angle. So we don't need that third one that I showed you in the last postulate. That was just to say, hey, if you do happen to have all three, you're done. They're similar. Okay, but by the no-choice theorem, this essentially says the same thing. Moving right along. Theorem 63 states that if there exists a correspondence between the vertices of two triangles such that the ratios of the measures of the corresponding sides are equal, then the triangles are similar. And this is side, side, side. But we add this at the end to show that it's only for similarity, because we're talking about the ratios being equal, not their lengths. So that's the big key difference here. So you can say side, 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 similarity. If you don't add that sign afterwards, then it is going to be wrong if you're trying to prove triangles are similar, unless they actually happen to be congruent. But for most of the problems in this unit, when you're trying to prove similarity, it's going to be two different sized figures that are in fact similar. So just please keep that in mind. So that would be if we're given that the ratio of AB to DE equals the ratio of BC to EF equals the ratio of AC to DF. So we're saying that AB and DE, the ratio of that is equal to BC over EF and AC over DF. That if you took all those numbers, reduced them down as much as you possibly could, that you would in fact get the same thing for all three. And you would be able to prove that the triangle ABC is similar to triangle DEF. Okay? Theorem 64. If there exists a correspondence between the vertices of two triangles such that the ratios, again, ratios, of the measures of two pairs of corresponding sides are equal, and the included angles are congruent, then the triangles are similar, and this is by side, angle, side similarity. Okay, now take a look. So let's say we'd be given the ratio of AB to DE were equal to the ratio of BC to EF, we would also need the included angle. Included, remember, means in between. So we've got this side and this side, this side and this side, so it would have to be angle B and E. And if we had that, then we could prove that triangle ABC was similar to triangle DEF. Okay, I can't stress enough. We're proving similarity, not congruence. Oh, I feel like I skipped one. I guess I didn't. Okay. So let's do a practice problem. We are given that ABCD is a parallelogram, and we need to prove that triangle BFE is similar to triangle CFD. So how do we do this? Start with your given. ABC is a parallelogram. Okay, when we have a parallelogram, we got to take into account what do we know about the properties of a parallelogram. Well, we could say that AB is parallel to DC because opposite sides of a parallelogram are parallel, which would then allow us to say that angle CDF, that right there, is congruent to angle E. And that's because if you have parallel lines, then their alternate interior angles are congruent. Then we could say angle DFC is congruent to angle EFB because vertical angles are congruent. And now we actually have enough to say that triangle BFE, don't mind that, is similar to triangle CFD by angle. Okay? So angle, like I said, is going to be the one you use the most because even with that, the angle, we didn't have the third one, but we didn't need it because of like with the no choice theorem, this can only be one measurement. And if these two are congruent, then the measurement for both of these have to be the same. So that's it for today. I just wanted to show you a quick proof of how you're going to use that. We're really going to kind of get into it a little bit more on Wednesday with how it helps you with actual measurements, other proofs, that sort of thing. So make sure you take notes. Don't forget about the quiz, and I will see you all when I see you.